All right, welcome everybody. And this week, for the past couple of weeks, we have been talking about this very interesting topic, zero knowledge proof. I think we covered quite a few, areas, and this is the last one, last session. I want to wrap this up and give you, I think, even more interesting use case for zero knowledge. So the idea is, you guys can take it from what you learned here and then use Script to build, kind of amazing apps we couldn't imagine now. Okay, so coming back, again, I'm showing this slide. I think we've been showing this again. So previously we have shown this, so-called this specific type of zero knowledge proof called ZK Snark is very amenable for blockchain use case because, so-called succinct. So we can use this, the short proof and small verification time. We can put it on the blockchain to a lot of times. I think the use case we introduced so far is mostly for hide the private input, which also called witness, right? So we can use it for, Zcash type of an anonymous coin or, or play kind of a, let's say, chess, incomplete information game. So we don't have to get all the information on chain, but still we can make sure the rules are being followed. Okay, I think there we kind of leave out almost like half of the use cases, and the other half I think I haven't mentioned, which I'm going to cover in detail today is, so the first feature for ZK Snark is, you can prove, this witness such that this evaluate to true, but also there's a big difference when you are when you're verifying the proof. So actually, this one is also called succinct because it's at least exponentially smaller, faster than the function itself. So for example, this function can be computing, let's say, 1 billion hashes, right? Like a chain of hashes. You take some number, you hash it like 1 billion times, okay? But usually let's say I give you X, I claim I have hashed it 1 billion times, and then give you the result Y. How do you check it? Whether this Y is actually the intended result. How would you verify it? Any proposal here?
What, using zero knowledge? You've given me a proof.
Okay, but then how? Okay, yeah, that's the idea. So, the naive way would be, what would be the naive way? Just, the typical way, people, you've never heard about this, how would you verify it? It's also very practical, right? You have a function, you can apply it to X, and then you outsource it to the cloud, right? Because F is super expensive, maybe the memory or CPU. Then you outsource it to some like a third-party provider, right? The cloud. And then the cloud finish computing and give it back the result. But what happened?
I don't know. You were on mute.
Yeah, okay. Froze.
Yeah, I think somehow the Zoom restarted, but whatever. I think let's keep going. I don't know what happened. Just randomly restarted. Okay, now we are back. You guys can see me. Okay,
yes.
Slide.
We can't see the slide anymore, though. We can just see you.
Oh, you cannot see the slide. Oh, let me share it again. I think you restarted for whatever reason. Okay, how about now? It's good. Okay, nice.
Yeah.
So I give you the example, right? So for example, I have a value X. I want to hash it 1 billion times. So and then because I cannot do it easily locally, maybe on my phone or my computer is not that good, I send it to the cloud, and the cloud compute it, I send the result Y back. But then how do I know whether the cloud provider is doing a good job? How do you check it? If you never heard about zero knowledge proof before,
you'd have to also hash it 1 million times and check the result.
Yes, exactly. But if you can even do it yourself, you don't need the cloud, right? So that's the so-called what we are going to cover today. So it's called you're using the feature. So here the function can be arbitrary, pretty much. It can be arbitrarily complex. It doesn't matter. And then if this is, let's say, big O(n), the complexity, this can be at least as efficient as log n, or sometimes it's just constant, big O(n). The
Hmm.
specific, some specific variant is just big O(n). So it doesn't matter how big the so-called computation or the circuit is, the verification time is always constant. So that means even this takes like 1 billion years to compute. So once you have the proof, I can verify it within like 1 millisecond. Okay. So that's what this. So this is not a big feature, right? It's not using the private feature. Now it's using the so-called succinct feature, the S, meaning, if I want to, it doesn't matter how complex the function is, I can always verify it very fast. Doesn't matter how complex it is. Make sense so far?
It makes sense what you're saying, but I don't see how it works.
Okay. Yeah. Here's the thing. I give you one example. How many of you heard about this term called roll up? Maybe you heard about other
Yeah.
blockchain contexts. So
Yes.
any idea anybody has a rough idea what is roll up?
So it's an Ethereum thing, isn't it?
Yeah, it's
I think.
it's pretty much holy grail for the so-called scalability
Yeah.
issue.
Is it? It's just
So
like an off-chain sort of. What do you call it?
layer two, yeah,
Yeah. Exactly. Yeah.
yeah, they call it that
An
way. So
aggregator.
basic
It sort
idea.
of aggregates all the
Mhm.
transactions, doesn't it? I think in some way.
Yes, yes, exactly. So I show one example here. So the idea is also is as the name suggests, right? So it's almost like you have a bunch of transactions. So for Ethereum or even for Bitcoin smart contract, if you have a state, you kind of if you have any kind of contract that has states. So what you do is, you know, you let's say you have 1,000 transactions here, right? So this state one, once you finish processing all of them, you go to a new state. Let's call it state two here. Okay. So the naive way would be, oh, you apply first transaction, you go to the intermediate state, you then apply the second, the third, and then until the thousands, right? So that's how it works. Let's say Ethereum, right? That's how it works currently.
So is
But
state
the
two
problem,
state n then, or is it actually state two? Because you
yes,
say you have a million
yeah,
different states in between or something.
yeah, state N right now.
Okay, yeah.
Okay, you can think of a state N. Okay. So the problem here is, if you have a sudden burst of traffic, a lot of transactions queued in the mempool, and then it takes a lot of time, and then you have high fees and high, delays, right? Which cause a user problem. Okay, and then you have to also pay high fees. So the solution they come up with is using this so-called ZK stack, but not using the zero knowledge property. So ZK stack pretty much you have two properties: zero knowledge basically means you're hiding information, keep it private, and then also succinctly, meaning the verification is exponentially faster than the computing it directly. Okay, so you can compute it directly here by applying all the each transaction sequentially, but then, as I said, right, you have a high cost on chain. But the idea is kind of like as the name suggests, you kind of roll them up into one single transaction, and this single transaction contains just one proof. So all of the transactions are valid, processed correctly. You process all this on off chain, and then you generate the proof. And then in one single transaction, you don't send, let's say, 1,000. You just only send one transaction. And this one transaction contains with it, the number one, the most important thing is zero knowledge proof. All these are processed correctly. So then the contract can just verify, hey, is this proof valid? If yes, I think all these are good. So I just go to the correct state. So in this way, you're kind of compressing 1,000 transactions almost like into one transaction. So that in that way, you can imagine you can improve the so-called throughput or transaction per second, right? Make sense here?
Yep.
Okay. So then in this case, a lot of people call it zero knowledge, but you can say this kind of like a misnomer, right? It's not using the zero knowledge proof. It's actually using the succinctness. But people call it, I mean, that's what most people call it ZK So it's not actually zk rollup. You see what I mean? It's actually, you can almost think a snark rollup. Okay. So let me actually go to more details here since we already, let's see. Can you see my browser?
Yep, we can see it.
Okay.
Yeah, I can see.
So basically, we implement the zk rollup natively on Bitcoin. Okay. So, this is almost like the holy grail. So that's the number one scaling. It's not sharding anymore for whatever reason. Or Casper. Yeah, it's been going forever. Anyway, so I just showed you this figure, but then let's show you one example here. So let's say you have a, let's say ERC20 token contract. Now you want to using rollup. How does that work? I mean, roughly. So basically you have on chain, you have a rollup contract. So instead of have, all the regional raw data, right? So basically if you think about it, let's say fungible token, what does it look like? So pretty much you have a table, right? Mapping each address to the balance, the number of tokens it has, correct? Okay.
Yeah.
So instead of storing that, you pretty much putting all of them in like a Merkle tree. So yeah, putting a Merkle tree, something like this. So you don't store the table directly. You just mostly store the root of the Merkle tree. So at each leaf, you pretty much have like address or public key, whatever, and then you have your balance. Pretty much others, yeah, some other meta information. But for this purpose, you can think of, each leaf contains the address and also the balance. And then in the contract, you just store the root of the tree. Okay. So then instead of all the players just broadcasting directly to the miners, you send it to the kind of like almost like a third party. Some people call it it has different names. Some people call it a coordinator. Sometimes it's called a sequencer. Pretty much you just send it to this almost like a middleman here, a batch of transactions. And then once you have enough transactions, you're going to like a roll up, almost like a batch, and then produce a proof. And then you generate one transaction. The transaction pretty much contains most importantly, what's the current root of the tree, what's the new state, the next, the next stage root, and then also like a proof. So if this validates, the rollup contract on chain validates this, it's going to update to the new state, which is the new state root. Okay, is this process clear?
Yep.
Yeah.
So not only we have the concept, pretty much we also implement, the contract itself. And this is the contract. Yeah, it's very simple. Pretty much what I just showed. You have the root of the tree, and then you can use a zk snark. Previously we talked about you can use the rules. The tools we have, for example, Circom or Socrates. So this is, for all the zk contract, it looks all very similar, but mostly it just give you the inputs, and then number one thing is you can verify it. So this one is always small and quick. Okay. And also we have the circuit here too. Basically, when I say this is a function is proving, basically you are validating each transaction. For example, you are checking, does the signature for the sender, does this check out? Or does the sender have enough, tokens in his account? And afterwards, the sender's amount is deducted, and also the receiver, is incremented, and then the root of the tree is updated. Yeah, just what you would imagine if you do this just even on chain. So pretty much you are validating the token transfer is valid. Okay, so this can all be coded in the circuit itself, right? This is the function we talk about. You are verifying a specific function. The function is this given transaction valid? And then when you want to roll it up, you pretty much put all the validation in a big loop, right? How many transactions you want to roll it up into? Is it 1,000? Is it 1 million? Is it 1 billion? Okay, so the only cost you pay here is the prover time, the time it takes to generate the proof. As you can imagine, right, the more processing you have, the bigger the prover time is going to be. So that's a cost you have to pay. Okay, but once you have that, doesn't matter how big the proof, how long the prover takes, the verify almost you can think of almost takes a constant time, like a 1 millisecond, or on chain it takes certain fees. Let's say 1 cent. It always the same. Doesn't matter how complex the computation is. That's the amazing part. Okay. So you are allowed to compress. It doesn't matter gigantic computation. It may take data centers hundreds of years to compute. But once you have the small proof, which is like 200 or 300 bytes, you can always verify it on your phone within a few seconds. So that's a big asymmetry people leverage to use for zk-SNARK. That's another big, besides privacy, so-called scalability. That's the another big use case here. Okay. Another question? For talk about scalability use case?
Yeah, I have one. So if you remember last time we had this this example with a code where you have 13 and 7 and you produce the proof.
Yes.
So the multiply was 91. If I'm not wrong, so you produce a proof for in this case, you produce a proof for 91. So that means that without showing that 7 and 13, you show that yeah. So if you need to create one proof for each item you want to. So if you want to do the same for 97 or whatever, and next prime you want to show, you need to compute another proof for that number, right?
Yes.
So it's,
even though it's the same circuit,
this,
when your inputs change, you have to recompute the proof.
So in the previous case with all the transactions, that means that I can create a proof to show that, for example, transaction 1 is included, but I will need to create different proofs in case I want to prove that more than one transaction is in there. I will need to create one proof per each transaction that I want to verify, right?
No,
not exactly.
because you could.
Yeah, go ahead.
You could send in an array,
go ahead.
couldn't you? I was going to say you could in that other example with the prime numbers. You could send in an array of prime numbers if you wanted, yeah.
But then you have to change the basically.
Yeah. I mean,
here.
if the circuit was different, you could send.
Yes.
So you could send in like 1,000 prime numbers and get 1,000 results. I mean, an array with 1,000 results in it.
Then you are using one proof to prove all the thousands of pairs of factorization. So it's like you can also roll up here. You see what I mean, right? You kind of compress. You are like a batching 1,000 if you want. So if you don't want to, let's say you have 1,000 such a pair, big numbers. You want to prove them at once. They can be factorized. You can just put a loop here for, let's say, from from 0 to 1,000, and then you put this is a new circuit, bigger circuit. Then you put all the witnesses in here. You generate one proof, and then you verify. If this checks out, for all the 1,000 pairs, it's good. It's the same here. It's like the transaction batching, a rollup we just talked about, right? I mean, in one circuit, you can verify one transaction, or if you want, you can batch like 1,000 or 1 million or 1 billion times if you want. Does this make sense?
Yeah, I think so.
It all depends what the circuit looks like. The circuit is just a function.
Yeah. So by but in this case, you will need to create this to prove the parameters you will need is 1,000 parameters, and then you will prove for the 1,000 being there. Yeah, I think I get it. Yeah, thanks.
Okay, yeah, that's good. All right. Any other question about the succinctness of the verifier? Okay. Then if not, let's keep going. So I think a very natural extension would be like, this is so-called, yeah, this is a little bit advanced, but it's very close to the idea we just talked about. After I explain, you should see the similarity, but it's not entirely the same. You can think about it, it's almost like one, this is almost like a generalization of the succinctness in a way. Okay, so previously we talked about, the function that we are going to prove can be anything, right? Okay, it can be arbitrary complex function, computation. But then, if you remember, we kind of flip on the head, right? The snark, when we verify a proof, the verification is also a computation, right? You're running some algorithm. It's like a ECDSA signature verification, right? It's certain computation. And then what if I put the verification also in a circuit? You see there, that's kind of a recursive, right? You're now, the circuit itself is proving some other zero-knowledge proof is correct. So that's a basic idea, how so-called recursive zero-knowledge proof, right? I think this is maybe a little bit of hard to wrap around, so I'll just give this one example, and then you should see. Let's say, you want to prove to a friend, okay, you went to some place. Let's say you go to, I don't know, Paris, for a week, okay? So what do you do? So one idea is, you go there on Monday, you take a picture at Eiffel Tower. On the second day, you go to, the Louvre Museum, you take another picture. And the third Wednesday, you go to all the points of interest every single day, you take a picture. And then at the end of the week, you send 7 pictures to your friend, right? I say, hey, this, I told you I was in Paris all week, last week, here's the proof, okay? But what if just a little bit hypothetical, right? So what if your friend or you are in some place where you don't have very good connection? Let's say all your friends saying, oh, you're sending me too much stuff. Just send me one picture. How do you use one picture? Just sending him one picture to prove you are in, let's say, Paris for 1 week. How would you do it? And any idea?
The picture was you holding the pictures. Exactly.
I think I'm not giving you the zero-knowledge proof. I'm almost giving out the result. Yes, that's the idea. So, as usual, on Monday, you take a picture in front of Eiffel Tower. On the second day, you go to like Louvre Museum. But then the only difference is while you are taking the second picture, you're also holding at hand the picture from Monday, okay? And then Wednesday, you do the same thing. You are holding the picture from, Tuesday.
And you're also holding a copy of the day's newspaper.
Yeah, something like that. Yeah.
But how do you know you haven't just taken them on the last day? How do you know you haven't taken all pictures on the last day, though? You were only there for 1 day. You just took 7 pictures with old copies of newspapers.
Oh, here's the thing.
That's, you take a screenshot with a camera roll.
Yeah. This is where the analogy, you can always cheat it. You can even Photoshop it. That's what I say. This is where the analogy kind of like a breakdown. But think about, you are not tricking. You are not like actively attacking your friend. Okay. I think, yeah, I get your point. You can be, in this case, even the proof is verified, it doesn't prove the original bounding. But that's, just bear with me. This is where the analogy is only good to a certain, to our assumption. If you're like really sophisticated, you can even Photoshop the whole
The only way you could do that would be to put it on the blockchain
put
it in the blockchain and include the latest block
hash. The hash, and then using the geolocation, somehow you can, you can
just put a photo up and include the latest block hash, and then you would know that you had been there for Because you'd be able to see what time
Yes.
you upload.
You can hash it in there. Yeah. So instead of the calendar here, let's say you put the, live the kind of a block height or whatever. So that's what some people do. Yeah. Timestamp it. Okay.
Yeah, you'd have to also
not...
upload it on the chain. Yeah.
Yes. Okay. So let's say given that, so you see the idea, right? So instead of 7 proofs, you can almost compress them, almost like a roll up a little bit into 1 proof. And then the amazing thing is, even I only get 1 proof, if this validated, I know all the 7 things you are telling me, right? That I know the whole week. Okay. So that's the basic idea. It's kind of recursive, right? That's called recursive zero knowledge.
Mm-hmm.
So basic idea is, let me show you again, just a refresh. It's kind of amazing. You think about it, it's also mind-boggling. So in this function can be anything. And also this verification is also a function itself, right? So in this, you're kind of like putting this back. Usually you're going this way, right? So now you are pretty much, you put this in the circuit or in the function you are trying to prove itself, right? So if you validate the new thing, that the old proof is also good. And then old proof can also contain other proof. So it's on a recursive, all right? So I know it's a little bit of hard to wrap around your head at the first time, but do you see what I mean here? So basically the function can be anything. So the function can also contain the verifier function. So once you prove this one is good, you also simultaneously prove for example, the input here can be the proof itself. And then the function is just a verifier. Okay. Usually this one is something else, right? Like a hash or let's say signature, whatever, or Sudoku or, factorization.
Mm-hmm.
But then verification is also an algorithm. You code it in F itself, which makes it recursive.
Mm-hmm.
Okay. Same page? All good?
Yeah.
Okay.
So is the verification function a circuit itself?
Yeah, you are coding it in a circuit.
Yeah.
You can. It's kind of expensive, but it's at least in theory it's doable, right? That's what people actually have done. But there are always ways to optimize, make it faster. But in theory here, you understand, right? It's possible because this function can be anything. So why not? It can also be the verifier too.
Yeah.
Okay. So that's a basic idea. I mean, we don't have to know all the detail how it's done, but you kind of get the high level idea, right? You are verifying a snack. This snack circuit contains a verifier for another snack. So it's like once you can verify the outermost proof, all the inner ones are good. Okay. So just give one like a more practical example here. That's what people in Ethereum world has done, which I think is interesting. So how many of you have heard about this? Let's say Erdos numbers in mathematics, or even let's say Kevin Bacon numbers in like celebrities. Anyone heard about this number?
I've heard of the Kevin Bacon degrees of Kevin Bacon thing. Yeah.
Yeah. Similar. Yeah. So basically, you can think of you have a graph, right? The graph at the center, there's some entity. You can have Kevin Bacon in like Hollywood, or can be Erdos in the world of mathematics. So then in this graph, that's like an origin. And then how do you almost like connect to the outer, expand the graph? So if you have a connection with Kevin Bacon, his degree he's like the center of the universe, right? Network. His degree is 0. This is the origin. And then if you, let's say in Kevin Bacon's case, if you have ever collaborated with him in any kind of movie, then your distance from him is 1, right? That means your degree is 1. You are 1 degree from him. Then if you are not 1 degree, and then you work with somebody who has worked with Kevin Bacon, then your degree is 2, right? It's almost like a distance, right? The number times you have to jump before you reach the origin. That's how it is defined in Kevin Bacon numbers, right? Make sense?
Yep.
So they do the same thing for in the world of Ethereum. So basically, they regard Vitalik as the origin, the god, in the world. So the degree for him is 0. So then, if you are a friend with Vitalik, then your degree from him is 1, right? And then vice versa, right? If you are a friend of friend with Vitalik, then your degree is 2, right? And so on and so forth. So the way you are proving the friendship is, they're using digital signature, right? Pretty much, they go there, hey, can you sign this connection for me? Yeah, like a attestation, right? And then I know we're really friends. I mean, that's how they define friendship for this application, which may always be like the friendship we think. Okay, so that's how the app defines friendship. Basically, you can get a signature from somebody, then you're a friend with him. Okay, so the idea is, this is kind of like a fun game thing. So if I go to a conference, I met Vitalik, he signs to me, then my degree is 1. And then if my degree is 1 and my friend doesn't know Vitalik, he asks me to sign, proof we are friends, and then my friend is distance 2, right? Make sense so far? This
Yep. So far,
numbers, how it's defined. Yeah. Okay. So here, how do we do this then? In using zk-SNARK. So basic idea is, let's say my friend, I have a proof, right? Saying, oh, Vitalik is my friend. I have a proof. My number is 1. Okay. And then when he gets a signature from me, then his number has to be computed, right? And then, so he has 2 things. One is my number is 1, and here's my proof. I also have to have a proof, right? Because the whole point here is, they want to do this using technology or cryptography. So you don't have to trust, right? I cannot just fake my numbers. Otherwise, it's not useful, not playful at all, right? So when I tell my friend, oh, I have my degree is 1, I have also give him a proof. Then with this proof, he also generated a proof. His number is 2. So if he can validate, my number is 1, I give him a proof, right? And also, if somebody see that I also sign for my friend, with these 2 things, then anybody who doesn't have to trust any of us, once he has this zero-knowledge proof, he can now be sure my friend's degree is 2. Make sense?
Yep.
Okay. It's almost like
it's a recursive thing again, isn't it?
Yeah, it's like computer science when you are doing almost like a Dijkstra, algorithm kind of thing. Similar, right? So when you are doing recursive,
what you are proving is that is at most 2, right?
Yes.
He could be 1 as well.
Oh yeah, I mean that's the point, right? If anybody who can be less, they'll be more bragging about it. So they will give me the proof for the 1. They will not give me for 2, right? That's bragging, right? Okay. So same again. You can expand this, right? If I have a guy whose number is n, also he can give me a proof, right? If I check this proof is good, I know he is n degree from Vitalik. There's no way he can cheat, right? Because of zero knowledge, you cannot cheat. And then if he has another friend, this friend wants to prove his degree is n plus 1. He needs to give me 2 things. One is he need to give me the formal proof of, let's say, the one who has n, degree n, and also the proof he's a friend with that guy, right? So this is the recursive proof, right? So if in order to prove you are n plus 1, you need to give me a proof of n plus, the friendship link, in terms of the signature. If I prove this too, I don't have to go all the way, and I don't have to find all the people from me, from the latest guy to the nth guy to the n minus 1 to 2 to 1 to Vitalik itself, right? I don't have to see all the former proof. You give me the last proof, and with the latest signature prove the link, I can be sure you are n+1. Okay. Hopefully this is make the more concrete. This make the recursive nature of the zero knowledge more, concrete. Make sense here?
Yep. So far.
Okay, great. Okay, you guys are smart. Okay, nice. All right. So, if anybody is watching here, or maybe you guys here, it will be a fun game. On Bitcoin, we have the beta version. So you can create, I'm X degree from Satoshi, call it Satoshi numbers, whatever, Satoshi dot number. And then if you go to conference, you ask Craig to sign it for you, you are degree 1. And then if your friend signs, you can get 2. Yeah, it's just a fun game for anybody. If you are watching here or live or watch it later, it'll be a good app, just fun game to play. But this is one primitive example. You can think of other use cases, which is not only for games, but it can for practical use cases, right? I don't know. I just think out loud. Maybe some cases you want to have some property, and this property also depends on some of your connections property. But you don't have to go all the way, right? For privacy reasons or for scalability reasons, for legal reasons. I'm just thinking of this loud. You can prove a lot of things. The good thing about it is this proof, once you have it, anybody who can check, he doesn't have to trust you. He can be confident. Okay? You're not cheating. All right. So, we just talk about, what is high level, what is it? Recursive zero knowledge. I just give you one concrete example. And then this only, I just show the big picture of why this also technology is super advanced. It's pretty much like cutting edge, but it also brings a lot of new features, amazing features. One, as I talk about, right? You can, instead of in the previous example, the proof, the recursive part is, I'm only doing it for one previous proof, right? You can also imagine in the function, in the circuit, I not only verify one proof, I can verify many proofs, right? It can be generalized. So, even in a, very generic case, let's say I have, let's say 1,000 proofs, right? I can kind of aggregate all of them. I put in a Merkle tree, I merge these two, and then I keep merging until I only have one proof. And this one proof, it's the same size pretty much the same size with all this proof. But the amazing thing is, and then on chain or whatever, even off chain, you can only verify this one proof. And if this one proof is good, all of this is good. Because you kind of doing this recursively, right? So this one is good, and then means this two is good. This one is good, meaning this is good. Same thing, you can apply, you can aggregate a lot of proofs into a single proof. Okay. So that has a lot of benefit you could imagine, right? For example, you don't even have to do roll up, right? You can do, so for each transaction, you can generate a proof, right? Saying this one is valid. And then for 1,000 transactions, you can aggregate all the proof. So previously it's like you generate one proof for 1,000 transactions, right? For here, you can generate one proof for each transaction, and then you can aggregate them afterwards. So only have one single proof. Okay? Make sense? Aggregation?
Mm-hmm.
Okay. And why do you want to do this? Then you may ask, previously you are generating one proof for 1,000 transactions, but here you are doing, for each transaction you generate one proof and then you aggregate them. One great benefit is you can then parallelize all of this process, right? Because previously you are kind of computing them sequentially when you generate the proof. I mean, generate proof, it can be very costly in terms of time and also resources. So if you can parallelize all of them, right, it will be much faster, right? You can do this, generate this proof, merge them together, all of this, because they're separate, right? They're independent.
Them, yeah.
So you can distribute it and you can parallelize them. So this is another big benefit. Why do you want to, do them separately and then merge them, right? So
I suppose you can also do them at different times. You don't have to do them all at once.
Correct.
It does it
for here.
Times.
Yeah. These are all like a mathematical function, right? all this computation is like deterministic. So it doesn't matter where you do it, when you do it, you can always do it. You want to merge this today, it's okay, merge it tomorrow, you run this computation laptop on that, on your cloud server, whatever, doesn't matter. It's all like, this is all deterministic mathematical functions. Okay, so that's why another thing I forget to mention about the, let's say, roll-up sequencer, or, you know, some people call it a coordinator. Everybody can spin that up, and nobody has trust them. You know, they call it censorship resistant or decentralization. Yeah, I don't want to go to that kind of term, but it's basically you don't have to trust all the sequencer because it's just a deterministic mathematical function. So once you have the proof, it doesn't matter. You don't have to trust. You can always verify easily. And also because it's deterministic, it doesn't have any kind of like state information or private information. That means everybody can spin up a server and to do that. So that also helps to, you know, kind of like avoid the single point of failure. Okay. All right. All right, cool. I think I will stop here. I think that this one is a little bit more convoluted. We don't want to go to the details since it's only wants to be like a introduction level, even though we already get very advanced here about talking about recursive ZK stack. Okay. Yeah, I'll pause here. Any other concluding questions or remarks for today? It's kind of amazing, yeah, the tech, the latest tech, yeah. And it's being like, yeah, every single day or week, yeah, you have some quite, you know, impressive update coming. People now are trying to do this specialized hardware to accelerate this. You could imagine almost like a hashing, right? They even put out $1 million price if you can speed this up, or using software or hardware. So it's called ZK price. So if anybody wants to interested, I'm going to put the link. So they're up to, yeah, the $1 million price out there if you can speed all this up, you know, significantly. Okay. Yeah, it's named after the X prize, which is also for like a moonshots projects. So this is like a moonshots project, but for 0.9, speed it up. Okay.
Are you working on it?
Oh, I wish, you know, I think it's very fascinating. I think it almost has to be like, you kind of have to be very focused on this because it's a lot of times it involves like a math and also very like a niche. If you know the certain hardware or certain elliptic curve tricks, you know, it's very, I would say, sophisticated. Pretty much, you pretty much have to spend a lot of time to improve it. It's almost like somebody come up with you and say, hey, I have this new miner. I significantly speed up. You know, my ASIC is much faster. I mean, like that's what people do, but there are not many people who in the world who can make that claim. You sort of mean? It's very cutting edge, really cutting edge. So if you really want to hone your skills, at least, I mean, for us, we are pretty much like users here. If you really want to get to the underlying math and stuff, start with playing with it first, get a sense, and then hopefully you can also, you know, improve the state of art. But that's like super advanced. Okay, but also interesting because it have a really lot of impact, right? Because if you can speed this up by 10x, you know, a lot of applications that's previously impossible, they'll become possible. Okay, any other things? All right, if not, you know, we can, that's the final section on 0.9, and next time we are moving to some other topics. Okay, thanks everybody for coming. Hopefully see you all next week. Okay.
Bye.
Thank you.
you.
Bye-bye.
Bye-bye. Have a good one. Okay, bye-bye.
Bye.